Hey, Dr. Seegren here, and for this video lecture, we are going to pick up where we left off last class. And where we left off last class was we were talking about Earth's place in the universe, how big the universe is, how big Earth is, how old the universe is, how old Earth is, and we talked about how Earth formed after a supernova. So that's where we're going to pick up today. So we know that kind of Earth formed after this supernova in this ball of gas that slowly condensed more and more, but it was really, really hot when it first formed. All these meteors were hitting it, all kinds of crazy stuff was hitting it. And so that is where we will start today, is how did it go from this hot ball of rock to this lovely place that we know now today. So let's hop right in. So we'll call this lecture Changes in Earth Over Geologic Time. And our kind of central guiding questions for us for this lecture are going to be basically, how did this transition happen? Our early Earth, 4.5 billion years ago or so, was not a very lovely place. You can see it looks extremely hot. Doesn't even look like there's any water. Meteors are constantly hitting it. Not a place you want to live. And then today, you know, hey, this looks kind of nice here. This blue and green ball floating out in space. So how did this happen? And some other things that we're going to think about here today with the thinker statue is how do we even know how old Earth is? I told you it was 4.5 billion years old. You know, I could be full of crap. You don't know if you can trust me. So we got to go over some evidence. How do we know what Earth was like back then? So I'm going to be talking, you know, I'm talking about how Earth looked like this 4.5 billion years ago, or 4 billion years ago it looked like this, or 3 billion years ago it looked like this. How do we know all that stuff? So that's some other central questions that we'll tackle today. And to answer those last two questions of how do we know all the stuff that I'm about to talk about, it largely depends on the subject of geology. And geology is a little bit different than other sciences. It's based off more evidence-based reasoning than experimentation. And the reason for that is that, you know, scientists do not have time machines. We cannot go back in time and see what Earth looked like 4 billion years ago. We have to really use context clues, like, you know, digging for fossils and whatnot. And so really it's a matter of trying to gather as much data and evidence as we can to get to our picture, rather than doing some kind of experiment like we learned about in the first lecture, where a lot of science is based off of doing experiments, not so much geology. And if you don't know the bottom right reference, go watch Bill and Ted's Excellent Adventure. All right, so let's get to that question of how do we know any of the stuff that we're going to be talking about today? Or in other words, how do we know how old all this stuff is, like the Earth and fossils and all that, rocks and all this stuff that we find on Earth? And ultimately, it's going to depend on chemistry and a concept called radioactivity. This, what you see below us, is actually a rock of uranium. So let's talk a little bit about this. And as kind of a refresher here, we're going to be talking very, very lightly on chemistry here today. But as a refresher, we have in chemistry, we have all these things called elements. And so every kind of bit of matter on Earth, so all the atoms of everything are some type of element. And what you might not know about elements is that they can change from one element to another. And a lot of times that's kind of glossed over in chemistry because it's more like nuclear chemistry. But, you know, we'll talk about it today. So these are not, just because you are made of uranium now as an atom does not mean you will be a uranium atom forever. So elements can change. That's the idea. And the kinds of elements that do change over time are called radioactive elements. And luckily for geologists and scientists, these radioactive elements act kind of like a clock. So these radioactive elements fall apart or decay over time, kind of like a clock. And that's actually what we're seeing in this picture. It's kind of wild looking. Let's pull up my pointer. Oh, that's a pointer. Is that a drawer or a pointer? All right, so what we're actually seeing here, this is a rock made of uranium there in the center. And what all these little things whizzing off are in all directions are little bits of atoms. So what's happening is that the atoms of uranium are breaking down, and in the process, they're shooting off little chunks of atoms in the process. And this is a special chamber that just lets you visualize that process. Normally, this would be invisible, and the scientists that worked with this stuff initially on didn't know how dangerous it was, and almost all of them got cancer. So that is what's going on. This is a radioactive element, a radioactive rock. And slowly what's happening is that these uranium atoms in this rock are slowly changing to another element. Remember, we have this periodic table of elements. So the uranium atoms here, they're losing a chunk of themselves. And as they lose a chunk of themselves, they are turning into another atom. And in this case, it's called thorium. So they're losing, and there you can see the little chunks are flying off. And the neat thing is that this is a very constant rate for some atoms. And if you have a pure radioactive substance, we say that the time it takes for half of it to fall apart is called a half-life. And so at some point, if we leave this rock sitting here, so much of this uranium will have fallen apart that we will have half of it be uranium and half of it will be thorium. Okay, and that would make it at its half-life. So scientists can calculate how long, so we can't actually watch a half-life take place because, unfortunately, for uranium-238, which I believe this is in the picture, this half-life is actually 4.5 billion years. So if we had a rock of pure uranium-238, and that's just a specific type of uranium, and we left it sitting there for 4.5 billion years and came back to it, half of the uranium would be gone and would be thorium. So that's a half-life. And it just so happens that the reason we know Earth is about 4.5 billion years old is because about half of the uranium is gone in Earth's materials. Pretty interesting. So when we look at the oldest rocks and we look at the ratio, that's ultimately what we're talking about, of uranium to thorium, we find that the rocks are about half and half. And that our assumption there is that Earth formed about 4.5 billion years ago. And the more thorium you have, the older the rock, and the more uranium you have, the younger the rock, is generally how this works. And this term we call rock dating because we are not taking the rocks out to a nice dinner, but we are trying to figure out how old they are, or trying to figure out their date. So that is a brief introduction to radioactivity, the chemistry of it, and how we use that knowledge to figure out how old rocks are. Pretty neat stuff. However, it does get a bit trickier. So when we're talking about rocks, that's all great, and we're talking about really old rocks that like formed at the beginning of Earth forming, that's great. But for everything else, it's a little bit, you can't use this simple of a technique. And the reason why is that in other words, living things are hard to date because to find out something's age, it must start out with a pure radioactive substance. So let's say you tried to grab a sample of me and figure out how much uranium and thorium I have. You could do that, and actually I probably would have tiny amounts of uranium and thorium in me, not very much. These are pretty rare elements on Earth, but they are actually around in very trace amounts. If I was like a Kazakhstani uranium miner, I would have a lot more in me. So already you can start seeing some of the issues with trying to figure out that kind of stuff for humans. If you look at my uranium-thorium ratio, it might be very different from somebody who works in a uranium mine because they have way more uranium in them because they're breathing it in every day. And so they might come out as being way younger than me. Oh, this guy working in the uranium mine is, 500 million years old, and Dr. Seegren is 5 billion years old. It's like, what? Just because we're not starting out with a pure substance in us. We're just kind of incorporating whatever. We're getting a little ahead of the subject, but basically you are what you eat. So mainly the atoms that make me up are what I've been eating recently and drinking and water and all that stuff. So because of that, you can't really get this start of a clock quite like you could with, say, like when Earth first formed out of the debris of a supernova. And that's literally when those elements first formed, was that supernova. That's a very easy clock to start. So that brings up the question, how can we figure out how old a life form is on Earth? After all, when you're walking through the museum and you see the Tyrannosaurus Rex, it'll say, 80 million years old, fossil. Well, they know that. So, the T-Rex doesn't have pure uranium in them to start out with. So let's talk about that. So to answer this question, it actually depends on another type of element, and that would be potassium and argon. And basically it's kind of the same as uranium, and essentially it changes a bit, and potassium can become argon. And we can look at those on the periodic table again, and it's kind of the same idea. Here's potassium is over here, it's K, and it falls apart and ends up, and it's just moving over one in the periodic table, but it just happens to be well over here on the other side to argon, which is technically the next one over. And so similar thing as our uranium to thorium. It's falling apart, it's changing over time. And this half-life is around 1.25 billion years. And a crucial thing with this uranium, or this potassium half-life, is that potassium is a solid, whereas argon is a gas. This is critically important for it because it has to do when rocks first form. We haven't really gotten into the rock cycle yet, but the idea is that we get new rocks. I think, everybody learns it maybe in middle school at some point, that we have these things called igneous rocks. As lava bubbles up from the earth, it cools down and forms new rocks called igneous rocks, and like lava rocks. I think we've all seen those in Home Depot before. And how this works is that argon gas, any potassium that might be in this lava here, if it happens to change into argon gas while it's still in the lava liquidy stage, the argon gas will escape out. And that means that the lava, as it's still liquidy, is 100% potassium because all the argon will be gone. So we have that pure radioactive substance in this liquidy lava. But as soon as it turns into this rock down here, the argon can no longer escape because it's trapped in the solid rock. And so as soon as the rock cools down, the instant that it cools down, the argon gas begins building up in it. And when it gets to be about 1.2 billion years old, if we look at a sample of this rock and we look at the potassium to argon ratio, it would be about half and half once it gets to about 1.25 billion years. So that's great. That lets us date fresh lava rock, and therefore we can date something besides just like when the supernova happened with uranium, but that still doesn't help us much with life, except it does. Volcanic ash works the same way. So all this volcanic ash is actually still kind of gassy and liquidy. So at this point, any argon that's made would still be able to escape this ash. And so this ash, basically, the actual powdery stuff, if we could isolate it, would be all potassium. And something you might not know about volcanoes and volcanic ash is that really, really big volcanoes will throw off a lot of this stuff. This bottom right picture, you can see there's like a village, I think, I'm not sure where this is, maybe Japan, and it's like completely covered in this ash layer. There are these things called supervolcanoes that when they blow up, they will cover like entire continents with ash. So there is actually a supervolcano in Yellowstone that goes off every 500,000 years, and it's potentially due, which is maybe that'll be a surprise in 20. But anyway, when this thing blows up, it will actually cover the majority of the United States in ash. So pretty much everything in the entire country would be covered up in volcanic ash when one of these goes off. Okay, well, what that means is that when you're digging for fossils, and let's say we found our lizard here in our layer right about here, what happens is that as we're digging for it, chances are we will come across a layer of volcanic ash. And that volcanic ash, we will be able to figure out the date of, how old it is. So if we find a volcanic ash layer of 170 million years here, and we know that layers get laid down like this, over time, the new layers are laid on top, we know this fossil has to be younger than 170 million years old. And let's say we find another ash layer up here that's 150 million years old, and the fossil is between these two layers, we know this fossil must be, but it must have died between these two volcanoes going off in the world to get sandwiched between those two layers. And so this fossil would probably be something like 160 million years old in this case. And that is basically how we know all of the ages of all the fossils that we're about to talk about next, as we talk about the history of Earth. Pretty neat. All right, so to quickly just run down the history of Earth, we know Earth first formed about 4.6 billion years ago, but we've actually divided Earth's history into 4 what we call eons, so big categories. And the first eon we call the Hadean Eon, and you might recognize this guy from Hercules. That's Hades. That's where this Hadean part comes from. And basically what scientists are saying is that Earth kind of looked a bit like the underworld, you know, a little bit hellish landscape. And obviously this is when Earth first formed from the nebula of a supernova. And it's pretty much assumed that no life was living on Earth at the time, that life could not be supported under such extremely hot and terrible conditions because the entirety of Earth was pretty much covered in lava. Anytime it began cooling down, there might be another big meteor that hit it and kind of heated everything up. There would have been some kind of atmosphere present, so a little bit of air maybe piling up around the outside. But it would have been really toxic and really hot. Certainly, if you had a time machine and went back and tried to walk out of your time machine onto this Earth, you would be dead in seconds. That's how inhospitable it would have been. Really not a lot happened back then because, you know, the Earth was still kind of forming. One really neat occurrence that happened was the formation of the moon, which we think happened about 4.5 billion years ago. The way we think this happened was that the moon actually used to be part of the Earth in the sense that it was made by out of the same material. And the way we think it happened was that a planet, maybe a bit smaller than Mars, actually ran into Earth and blasted off a chunk that then reformed into the moon. And I'll show you an animation of what that would look like. All right, some of the evidence of this occurring, why we think this occurred, is that the moon and spin and the orbit are pretty much in sync. So we're always looking at the same side of the moon. And if you think about it, if the moon was made of Earth's kind of initial rotation, that's how it would work, basically. And also, probably the most compelling and easy to understand evidence is that the Earth and the moon, when we went up to the moon and we looked at some rocks, we were like, oh, these are pretty much the exact same rocks as we'd find on Earth. They're chemically identical, and they're all pretty much igneous rocks, which means that they're made of molten lava. They don't have any, there's no volcanoes on the moon. The idea is that the moon, this chunk of Earth that blasted off, was basically all melted rock, liquefied rock that then cooled to make the moon. So makes sense. So after the moon, the eon that we say comes next, and there's two major events that kind of happen pretty close simultaneously. We don't really know exactly. They're both around 4 billion years ago. They might be a bit more or a bit less. But we're pretty sure that water at some point began pooling on the Earth, and that Earth began cooling enough to support water. Where water actually came from is a bit of a mystery. There's a couple kind of theories, and they both might be right. When you think about water, it's just hydrogen and oxygen, H2O, right? And hydrogen and oxygen are really common elements found in all kinds of rocks. So in the right conditions, it's possible that these elements sort of just were kind of released by rocks and formed water. I think the more probably realistic explanation for where water came from was actually meteors. A lot of meteors out there, if you are looking at a comet and it has this kind of trail coming off of it here, behind it, most of that is actually melting ice that's leaving that trail. And so we find water is actually pretty common on asteroids and comets and meteors and all that stuff. So in the early days of the solar system, there were probably a lot more asteroids, and so there was probably a lot more water floating around, and that might be where it came from. Anyway, regardless of where it came from, we got water about at least 4 billion years ago, maybe a little bit more, and this marks the beginning of what we call the Archean Eon. And again, now Earth is no longer, kind of hell on Earth like the Hadean Eon, where everything's lava and hot, but now we actually have some cooler temperatures, we have some water, and not long after that, we actually get our first evidence of life. And our first life form was the mighty kind of algae-looking thing. Basically, bacteria and algae would have been sort of the first life forms on Earth. There might be some people that are nitpicking that. It's probable that they didn't do photosynthesis, so technically not algae, more like bacteria. But these are what the first fossils look like. They're these little things called stromatolites, and they actually still form on Earth today. This is what the modern day stromatolite looks like. And basically you get some bacteria and algae kind of growing in the mud. And when you have water and waves and wind kind of hitting this surface, the bacteria and algae kind of stabilize and hold on to their mud, and everything else kind of gets eroded away out into these crevices, and you're left with these little domes hanging out on the side of the ocean, and that's a stromatolite. And the fossils look like this, and we can use our dating techniques, our rock dating techniques, to say that they're around 4 billion years old. And the assumption here is that these stromatolites could not have formed if there was no algae and bacteria present, because we don't know of any stromatolites that form today without algae and bacteria. So it's not impossible that there was just some different type of formation forming back then that didn't have any algae on it, but that's the assumption that scientists make. And so generally it's accepted that life started about 4 billion years ago. And Here, after about 1.3 billion years after the start of the Archean Eon, we get what we call the Proterozoic Eon. And this is marked by oxygen being present in the atmosphere. So before this, we thought there was no oxygen, not enough to support modern day animals and life forms in the atmosphere. And something else that's going to be maybe a little bit confusing is that as we move forward in time, our numbers are going to get smaller. So I said we went from 4 billion years ago to 2.7 billion years ago. 1.3 billion years have gone by. So we are 1.3 billion years more present now. And that's why our number went down by 1.3. So as we move through this, the numbers are going to get smaller and smaller. And where did this oxygen come from? Well, we're pretty sure it came from these guys. So as these algae were growing, and at some point they figured out how to do photosynthesis, and photosynthesis takes sunlight and produces oxygen out of carbon dioxide. That's where all the oxygen came from on Earth. So next time you take a deep breath, pretty much all that oxygen would not be there without these early stromatolite forming algae of the early Archean Eon. So there you go. Thanks, algae. So in this time period of the Proterozoic, now that we have oxygen, we probably do have some other types of life forms existing, but they were all, for the most part, probably microscopic. And when you're that tiny, you don't really leave fossils behind. So this stuff probably was living in this time period as well. We just don't know about it. Something else that's kind of neat, about 1 billion years ago, so still in the Proterozoic Eon, we do have the first seaweed. So it's not just algae, but actually seaweed's kind of like an algae that's sort of formed a bigger body. And it's still very simple compared to something like a plant, but it's more complex than an algae. And this is also, in this eon, we would have had our first fossil evidence of things that kind of resemble animals. This looks a little bit like a fried egg, this gabbonite. This is the fossil right here of what they look like. This is what we think maybe they look like in real life. And we're pretty sure they didn't move around or anything. They're probably most similar to something like a coral or a sponge today, but we don't think they're plants. And this one is really interesting. This is the fossil's called Dickinsonia, and this is about 600 million years old, this fossil. And this is the fossil, looks like this. Maybe the animal looks like this. We're not sure if it could move or not. This is kind of like a shell. Modern day, we kind of have something like this that looks, I would say that this kind of looks like a limpet, which is sort of like a clam that only has a shell on one side. So maybe that's kind of what it was like, although it's unclear if this actually moved around or not. So if we could take a time machine back to life back then, there wouldn't be a lot going on. We would have water, we would have bacteria, we would have tiny microscopic creatures, we might have some very simple seaweeds and maybe some kind of sponge corally looking animals. But that's it. It would be kind of a foreign world to us in a very simple world. And you might have noticed that we went to 600 million now. So here we're underneath a billion at this point. This is younger than a billion, considerably. And what this means is that for the vast majority of Earth's history, about 4 billion years, the Earth would have been pretty unrecognizable. Then around 550 million years ago, or to be precise, 541 million years ago, is where we define the last eon, the Phanerozoic eon. And this time period in the fossil record is highlighted by a massive diversity of life forms and things that you might kind of recognize today. So these are trilobites, but they kind of look like maybe horseshoe crabs or something like that. This looks kind of like a centipede or something. It's got like pairs of legs. Unclear if it swims around or what. This looks maybe like a jellyfish or an octopus a little bit. Here, this is much more clearly. It's kind of got a head and it's got little mouth parts, and then it's got a body here. That's very much like a modern day kind of centipede looking thing. Same with this one, a little worm-like, a couple worm looking things here. And so we start seeing things that are beginning to be recognizable. And if we could time travel back to this world, I think, it would be strange, but it wouldn't be all that foreign. We would recognize things. It wouldn't just be that barren world with really nothing going on in it. And the scientific term for this is the Cambrian Explosion. I'll get to what Cambrian means in a second. And the explosion part doesn't mean literally like a volcano or a meteor. This means an explosion of life and life forms that we begin seeing at this point in time. And so just to kind of summarize the eons, the Hadean eon and this scale here is roughly proportional to how long it actually lasted on Earth. This is when basically, everything was lava. This is not easy to write with my mouse. And so there was no life then. The Archean Eon was marked by water and life, probably water first. But this life was simple, like bacteria and algae. That was pretty much it. If you could time travel back to then, there would be, nothing really recognizable. The Earth would just be kind of like pretty boring, just some algae and bacteria living in that whole time period. And again, that span of Earth's history is 1.5 billion years long. So a massive amount of time where there just wasn't much going on. And then we almost have another equally long time period here where we start getting oxygen and we start getting the beginnings of things like seaweed looks like I'm in kindergarten again. Seaweed and things like maybe a sponge or coral. So very simple plants and animals. Probably could have just said that, not tried to write it out. And again, that's another billion-year long period there. And pretty much everything that you would recognize in Earth's history have fit into this last 500 million years or half-billion-year period. And this is when you get all the fish and dinosaurs and amphibians and mammals and birds and plants and all trees and all that stuff all basically gets crammed into this last little phase, which we call the Phanerozoic Eon. And you might notice that this is actually the most paid attention to time period by geologists because we have all these additional breakdowns of names. We have eras, Cenozoics, Mesozoics, Paleozoic, and then all kinds of periods. We have all kinds, like you've probably heard of one of these at least. Jurassic is the middle of the dinosaurs. The reason for this is that this modern era, the Phanerozoic, is all defined by what kinds of life forms lived when. And it kind of gets a lot of attention. So again, how do we define these more recent time periods on Earth? It's pretty much all based off of fossils and life forms. And We call these fossil assemblages. And the idea is that if you're digging in some sediment and you find this is a trilobite fossil, that's what these are called. They kind of look like little crabs, and we think the actual animal looks kind of like this, so kind of like a modern day horseshoe crab a bit, if you know what those look like. All of those fossils, when we date them using the volcanic ash technique, they all pretty much live in this window right here. This is where all the trilobites live, right in this, roughly in this era. And they really are dying out by the time we get much further than that. So the idea is that actually now that we know a lot more about fossils and the different eons and eras and periods, if we find a trilobite fossil, we're pretty sure it's in that 500 million year old range. And if we find a fossil next to it, where you can be pretty confident that that's also 500 million years old fossil. So that's what we use to define geologic periods, and also it can be helpful as a technique to age something or to date something. All right, and quickly through, just running through different events that define different periods and eras. Fish, we've found the oldest fish fossil corresponds to about 440 million years old, and these were kind of strange looking fish, and they didn't have modern day fins, and they had these big hard heads, and the idea is that they needed protection against things like sea scorpions, which were the dominant predator at the time. Very different world, but still kind of recognizable. We also started getting actual plants living on land, so no more just seaweed in the ocean. We actually have plants that can root themselves onto land. Very primitive, these are called liverworts. They actually don't have much of a root system at all, and they have to be living in a very, very wet area to survive, but nevertheless, plants. And of course, now that you have plants on land, that also helps support things like insects on land. You have a base of the food chain now on land, so other things can start moving onto land as well. 380 million years ago, we had jawed fishes show up, and mainly I include this one just because of how cool this fish looks. This is like the first sort of shark-like creature, maybe we would call it, but super bony head compared to most fish, and instead of having individual teeth, its teeth are kind of all together on this bony plate. Pretty neat. 340 million years ago, and notice that we're getting smaller and smaller in number as we go along, because we're getting closer and closer to 0 million years old ago, which is present day. So 340 million years ago, we had our first amphibians. So no longer is it just fish in the ocean. Now we actually have things roaming the lands along with pine trees. So those early plants figured out how to build roots and actually anchor themselves to the soil and get water from the soil. And so now they are kind of freed from being confined to watery areas and can kind of spread out a bit onto land. And you also have insects on land as well. So this is if we were a time traveler going back to this time period, I think we could recognize this world. Well, with the exception that the insects at the time, because the air was much warmer and actually the oxygen content was a bit higher, insects seem to grow way bigger in this time period. And this dragonfly here is about 2 feet big, wingspan, and even crazier is this centipede guy up here who's fighting this frog monster if the average human is about 6 feet, these were about 8 feet long. So if you can imagine walking around in the woods and coming across an 8-foot long centipede, well, that'd be kind of creepy. 252 million to 66 million years ago was the age of the dinosaurs, so that whole time range would be dominated by dinosaurs on land, and dinosaurs were reptiles. First mammals actually would have been after the dinosaurs, so about 160, but notice 160, you have to kind of use your noggin here a little bit. 160 is within this range, right? So that means that dinosaurs were around when the first mammal came into existence. And so this little squirrel guy here, we would call it a tree shrew, would have potentially been eaten by dinosaurs. Watch out. The first birds also came into existence about 150 million years ago. So also in the presence of dinosaurs. And actually, when you look at this first bird fossil right here, and this is what we think the real organism looked like, we notice this is a tail, and you can see these are feathers coming off of the tail, like this, all those little lines there, that imprint. So it had a long bony tail, and I don't, you may or may not know this about birds today, but they do not have an actual tailbone in their tail feathers. It's just all feathers back there for modern day birds. Also, if we look at this guy's skull, it does not have a beak like a normal bird, but rather teeth like a lizard. And so we would call this a bird, but in reality, it's kind of, it's sort of half lizard, half bird. And actually, it's half dinosaur, half bird. Birds were a direct descendants of dinosaurs. So birds are related to dinosaurs. They are modern day dinosaurs. Something that's just kind of crazy that's also neat to think about is that we actually had dinosaurs on planet Earth before we got any flowers on planet Earth. I know we kind of think of maybe plants as being more primitive or maybe coming first or something, but actually, just as everything else was changing, plants were changing too. And we had no flowers before 130 million years ago. And lastly, we should cover briefly the idea of a mass extinction. So the end of the dinosaurs, I think famously we know a few things about. That happened about 65 million years ago. And we're pretty certain that this was a massive meteor impact. And it left a massive crater, which is actually in Yucatan Peninsula in Mexico. That's where it hit. And this meteor would have been so big, not only did it leave a massive crater, but it would have caused an enormous tsunami. Anything nearby it would have been almost instantly killed. But also, really important thing is that when this thing smashed into the Earth, it was moving so fast that it would actually punch a hole in the Earth's crust down into the lava layers underneath the Earth, which we'll cover more later in the course. And that disrupted volcanic activity all over the planet, more than likely. Also, all this junk, all these rocks and dust would get blasted up into the air. And this stuff that got blasted into the air would quite often make it out into outer space, but not be blasted so far that it would actually leave the orbit of the Earth. And so all this stuff would come raining back down as kind of like a fiery rainstorm of small meteors and stuff. So the thought is that all this stuff would actually have superheated Earth for a time. And then the smaller dust stuff would then have blocked out the sun, kind of like the fires in California are doing today. And so you basically have a massive tsunami, probably increased earthquake and volcanic activity, a rain down of smaller meteorites that would heat up the atmosphere, and then followed by a blocking out of the sun for a pretty long time period. So this was a horrible event, and pretty much everything died. So it definitely killed off the dinosaurs, and 75% of all species on Earth, all types of different plants and animals, died as a result of this. And the interesting thing is, you might be asking, wait, what? Fifth and final mass extinction? What about all the other ones? Yes, there were 5 of these kinds of events that have happened over the course of Earth's history in the Phanerozoic Eon. So in the time period that we actually had life and lots of fossils, we've had 5 mass extinctions. And these are indicated by basically, you find lots and lots and lots of fossils, and then a whole bunch of them disappear. And the idea is that that is a mass extinction. So if we're looking at what's called the extinction rate over time, how many things are dying off, we have these 5, 1, 2, 3, 4, 5 spikes. And this 5th one is the dinosaurs dying. So that famous event that killed the dinosaurs, there were 4 other ones that were similar to it. And these things, they're a bit mysterious what happened. Probably is a combination of volcanic activity, meteors, and climate change that would drive all of these extinction events. So after all the dinosaurs died off, it opened up a big kind of new reality on Earth where you didn't have these massive dinosaurs to compete with, and mammals sort of filled that those ecological niches, we would call them. And so in the last 65 million years, we would call kind of the age of mammals, although it's not quite true. There's plenty of other reptiles and birds and fish still doing just fine today, but that's what we would call it. And all kinds of really neat creatures lived in this time, including us. So we would have shown up in the fossil record about 160,000 years ago, which is less than a million years old. This video has probably already gone on long enough, but that pretty much walks you through, well, the last video we watched was how Earth formed and sort of its place in the universe and how old it was. This video was about how do we know how old it is and what kind of changes have occurred over time. And basically what we see is that for about 4 billion years, the first 4 billion years of Earth's history, there wasn't a whole lot going on. We got water and we got some life forms and we got some oxygen. And then we barely got some like seaweeds and sponges and corals. And that was about 4 billion years. And then in the last 500 million years, we got lots of stuff. We got fish, we got frogs, we got big insects, we got plants on land, we got trees, we got dinosaurs and mammals and birds and flowers and all this stuff. That was all crammed in towards the end of Earth's history. And again, humanity would be the tiny speck on the very end of your timeline. So hopefully that kind of puts things in perspective on what was going on Earth and where we fit into it all. And the next lecture is going to be focused on this last tiny little section of the timeline of humanity. So basically human history. How have humans changed over the last 160,000 years? And how have we changed Earth? And that'll be a pretty good introduction for environmental science. All right, well, I'll see you later. Stay safe.